Okay, this is my video number 13. Right, in this video I'll talk on the non-homogeneous Volterra integral equation. Yeah, non-homogeneous Volterra integral equation. Integral equation. So at the beginning we will develop some theorem, then later on I'll discuss on the example. Okay, for the this lecture I think I just give you some related theorem on the solution of the non-homogeneous Volterra integral equation. So for the Volterra integral equation, we have the general form is given as ux fx plus integrate from 0 to from some number a to x k xt ut dt, and the iterated kernel, as we have seen many times, yeah, iterated kernel we have k 1 xt is k xt, and kn xt, this is defined as for the Volterra we have a to x. What happened? Suddenly it's dark. Just a minute. Alright, okay. My laptop is off. Just a minute. So where is it? Okay, so kn is given as we have k x s kn minus 1 st ds for n equal to 2, 3, 4, 5. So basically the iterated kernel for the homogeneous Volterra integral equation and homogeneous non-homogeneous Freedom integral equation just the same. Okay, so this is the iterated kernel for the Volterra integral equation are also called as the approximate kernel or approximate function. Yeah? We call it as approximate kernel or approximate function. So let me write those things. This is also known as approximate kernel. And then for the resolvent kernel, yeah, for the resolvent kernel, we have ux. So the solution of the Volterra integral equation can be written in the form of ux fx plus lambda integrate a to x r x t lambda ft dt, yeah, or you can use gamma xt lambda. So what's the difference between the Volterra and Freedom integral equation is the limit of integration here. Yeah, for the Freedom we have a to b, so both are some constant. Now for the Volterra we have limit from constant to some variable. So the same thing for the kernel, the same thing for the resolvent kernel. Okay, so the resolvent kernel, in this case, this R and T here, yeah, this is called as a resolvent kernel. Yeah. So we look at how the solution look like for the Volterra integral equation. Yeah, by using the successive approximation. solution of non-homogeneous Volterra integral equation by successive approximation. Successive approximation. We have a theorem okay, so we have a theorem. So for we consider the Volterra integral equation, which is of that form. Let me write this again. So we have ux equal to fx plus lambda integrate a to x kxt ut dt. And so the kernel k, with the properties that the kernel k is real and continuous on some rectangle R, where R is a point xt such that x in AB, in AB and t in AB, and also the kernel is bounded. Kernel is bounded. So bounded means the magnitude of kxt, this is less than equal to some m in R. And our assumption number 2 is that the function fx is different than 0 and it is continuous, real and continuous on some interval I, where I is all x such that x in AB. Yes. And also f is bounded. F is bounded in such a way that the magnitude of f is less than n in I. And the third assumption is that the lambda is a constant such that the magnitude of lambda, this is less than 1 over m b minus a. Alright, then the integral equation, the non-homogeneous Volterra integral equation, let's call this equation 1, say, has a unique continuous solution, and given by ux is equal to fx plus lambda a to x kxt ut dt plus lambda squared a to x kxt integrate a to, I think here a to x, here a to t, I think a to t, k x t1 f t1 dt1 dt2 and so on. Okay, so let's prove this. Let's prove this. So we prove that. So remember the solution of the Volterra, the non-homogeneous Volterra integral equation is given by that, where this series absolutely and uniformly convergent. Yeah, this series is absolutely and uniformly convergent. So to prove this, so the Volterra integral equation that, so we can write this if I can change the dummy variable, yeah, or the variable for the integration with let's say t1. So let's write those things. Let me write those Volterra integral equation again. So we have from the Volterra integral equation, we have fx plus lambda integrate a to x k xt ut dt. Okay, so if I can change t with t1, so what we have is that ux is equal to fx plus lambda integrate a to x k x t1 u t1 dt dt1. All right, and if I change x with t, so what we have is that ut is equal to ft plus lambda a to b k t t1, sorry, a to x. Here we have a to t, sorry, a to t t1 u t1 d t1. So the purpose of doing that is that we are looking for the solution of the Volterra integral equation, where in the solution it should satisfy the Volterra integral equation. So in order to satisfy those things, we need to substitute this ut. All right, so so what we are doing now is that try to substitute this ut. So we have this ut is given as that. Just substitute into that. So what will happen? So let's call this equation 1. Let's call this equation 2. So we substitute 2 into 1. 2 into 1. So what we have is that ux is equal to, we have fx plus lambda a to x k xt ut. Our ut is given here, so we have ft plus lambda integrate a to t k t t1 u t1 d t1 dt. Okay, just substitute everything ut with equation number 2. Then we can simplify those. That will give you, we have fx plus, we have this is lambda integrate a to x k xt ft dt plus, now we have lambda squared. So lambda squared integrate a to x k xt integrate those a to t k t t1 u t1 d t1 dt. Okay, so again I can substitute this u t1 using 2. Right? So if we use 2, you have that's ut, just a minute. So we have ut is that yeah, change t T1 with T2, change T1, we change into T2, then we have X into T. So what we have now is that UT, we want UT1, so you have UT1, this equal to F T1 plus lambda A to T1 K, we have here T, T1, T2, then we have U, T2, then we have D, T2. Okay, so let's call this equation number 3. This is 3, this is 4. Now we substitute 3 into 4, 4 into 3. Again, we substitute. Let me use other papers. Let me use new papers because we have quite long derivation there. So we substitute 4 into 3. So what we have from equation 3 here, we have ux and everything, but we need to substitute from that. This is our ux. So we have everything except that ut1 we substitute with this. Okay, so we have ux is given as fx plus lambda a to x kxt ft dt plus we have lambda squared integrate a to x kxt integrate a to t kt t1 tt1 and then ut1 is we have f t1 plus lambda integrate a to t1 k t1 t2 u t2, we have dt2 and then we have dt1 dt. Okay, then we simplify this. Okay, simplify this. So what we have, this is fx plus lambda a to x kxt ft dt plus we have a lambda squared here, lambda squared integrate a to x kxt integrate a to t k t1 f t1 dt1 dt2, sorry, dt1 dt1 dt, right, plus we have lambda cube. So for the lambda cube, that so we have integrate a to x kxt integrate a to t kt t1, and then we have another one here integrate a t1 k t1 t2 u t2 dt2 dt1 dt. Okay, so observe that from here the solution is of that form where the first term is fx, second terms we have lambda, third term we have lambda squared, we have lambda cubed. So it's in order. And in terms of the integration, we have a to x here, k and f, and the second term we have two kernel here, where the integration is 0 to a to x, a to t, and the third terms we have three integral with three kernels with kxt, kt1, kt1t2, and ut2. Okay, so we can generalize this. Okay, if we proceed this up to n terms, and again proceed up to many terms to infinite, so what we have an infinite series, which is given as, so if you proceed this, so we have ux is given as fx plus we have lambda a to x kxt ft dt. That's for the first term. The second term we have lambda squared integrate a to x kxt integrate a to t kt t1 f t1 d t1 d t2, and we have the third terms that, and we have the fourth term, and so on. You can proceed this up to n terms. We have lambda n, n term we have lambda n integrate, basically this is term n plus 1 because the first term is fx. So here we have a to x k xt, then we have integrate a to t k t t1, then we have integrate a to t1 k, we have for this we have t1 t2, so we have t1 t2 and so on. Integrate a to t, we have lambda n in there, so n minus 2 k t for 1, for 3 we have 1, so we have tn minus 2 tn minus 1, and we have d2, so we have d t n minus 1 dt n minus 2 and so on, dt 1 dt, and plus we have some, this is for n plus 1 terms, then we have n plus 2 term, which is given as, let's write that as a rn plus 1 x. Okay, where rn plus 1 x, where rn plus 1 x plus 1 x, this is equal to, so let's call this equation, I have 1 2 3 4, this is, let's call this equation number 5, where rn plus 1 we have lambda n plus 1 integrate a to x kxt and so on until we have a to t n minus 1, right, n minus 1 k t n minus 1 tn f tn dtn and so on, d dt, dt1 and dt. Now if we consider the infinite series, so this series here, this is infinite series, we have fx and that terms, and that terms, and that term, and so on. Those are infinite series. So if you consider that, okay, let Tn x so represent that series. So no, sorry. So we consider the infinite series. Consider the infinite series that we have here, fx plus lambda a to x kxt ft dt plus lambda squared integrate a to x kxt integrate a to t kt t1 f t1 dt1 dt and so on. Alright, then we let the n terms, let's call that Tn of x as lambda n integrate a to x k xt a to t k t t1 and so on up to n terms. So we have a t n minus 2 k t n minus 2 t n minus 1. So we have f t n minus 1 d t n minus 1 up to d dt dt1 and dt. Okay, now if you take the absolute values both sides of this, so we have this is Tn x, we take the absolute of those, so we have this is lambda n integrate a to b absolute of kxt integrate a to t k t t1, okay, and so on, integrate a to t n minus 2. We have here k absolute of k t n minus 2 t n minus 1, that, and absolute of t f t n minus 1 and dt1 minus 1 to dt. So dt n minus 1 up to dt. Now, from the given assumption in the theorem that the magnitude of the kernel is bounded less than some number m, and the magnitude of f also bounded less than some number n. So what you got is that we have this is m, we integrate respect to t, first thing inside here, of course, this is n less than n, that one less than m, and then we integrate t to minus 1. So we have basically all this thing less than, so we have lambda n, for those we have n, and we have that m, and last up to here, that terms, if you do one by one, you have b minus a, and we have n times n, and each of those we have n factorial. Okay, so you can write. So basically we have, what we have now is that Tn x is less than n lambda n, we have m b minus a n over n factorial. So therefore the series that we are looking for, that I mentioned earlier, where is it? So f. Okay, so therefore this series here, so let's call this 5, this is 6, let's call this 6. Okay, so therefore for the n terms is converge, yeah, for the n terms is converge, then we can say that the n minus 1 terms converge, and so on up to all this term, so it's converge. So therefore we have those equations 6, therefore equation 6, or the series 6 actually, series 6 converge if the n terms, those Tn x less than lambda n, and we have m for any x, so this is x, supposed to be x here, sorry, I did mistake here, this should be x, yeah, a to x for the volterra, so here should be x as well. So here is x. So we have x minus a n over n factorial, yeah, for x between a and b. So that's the condition for the convergence of that series. So therefore the solution of the volterra integral equation, I wrote somewhere, not this one, just a minute, where is it? Yeah, the solution, which is this, because all terms converge, so means that ux, we have the solution is also converge, yeah. So the series for which the positive constant, that positive constant is general expression for the n terms is convergence for all value of lambda n and m b minus a. So therefore it follows that our solution is also converge, and absolutely and uniformly converge. Okay, so thus if the equation, the volterra integral equation has continuous solution, then it must be expressed in that terms. If it has a solution, continuous solution, then the solution must be written in that form. Okay, so if u is continuous and absolute value has a maximum value p, say, so this is about the solution. If ux continuous and bounded by some numbers, let's say ux less than some number p, then from Rn, we take this Rn, we take the absolute value of this, and we have here is lambda n plus 1, we have k everything here, so this is m, that give you m b minus a to m plus 1 over m plus 1 factorial, and we have terms p because of u here. So what we have is that we have so therefore we have n plus 1 x, this is less than equal to lambda n plus 1, we have p and we have m b minus a n plus 1 over n plus 1 factorial for x between a and b. Then of course from there, if we take a limit, n goes to infinity, so of our nx, n plus 1x, that gives you 0. So therefore the solution of the non-homogeneous Volterra integral equation satisfy the solution that we mentioned earlier. Where is it? That satisfying that is a continuous function. Okay, so that's the solution for the successive approximation for the Volterra non-homogeneous Volterra integral equation. Alright, so I think I stop here for this video. Next I'll give you another theorem using Newman series. Then after that, then I'll give you example. Yeah, for I think for now we stop here. Okay, thank you. Bye bye.